But let me talk a little bit about exothermic desorption or endothermic desorption. This is a funny looking plot, but let me describe the problem more simply. If you have hydrogen or deuterium, it can either be outside the metal or it can be inside the metal. If it's outside the metal, it's got a good chance of being in a molecular form. And this graph here, this distance is the distance above the metal. And this valley right here are the two hydrogens being separated by not very much. So right here, the two hydrogen atoms, the deuterium atoms being a molecule. When the molecule approaches the metal, depending on the details of the metal, the molecule will break apart and go in and be atomic hydrogen inside the metal. And that's what's going on in here. And between here and here, there's an energy barrier. Namely, it takes more energy for the hydrogen to be in this regime. And it's in this regime, it's busy coming apart. This basic picture, this plot's for copper. In the case of copper, the hydrogen is a very high energy point here, and it's a lower energy point here. And so what that means is when the hydrogen goes from here to there, it gets a kick. It's going net downhill. I mean, maybe there's some hills and bumps and stuff, but by the time it gets out, it's picked up some energy. It's like you start at the top of a hill on a skateboard, and you go down, you convert potential energy into kinetic energy. Well, same kind of thing happens here. When you get out here, you've got this kinetic energy, so the molecule gets shot away. Now, it turns out that this is really interesting because this is, to some degree, the kid sister for how excimer lasers work. Excimer laser starts out with two molecules that don't, or two atoms that don't want to make a molecule, like krypton fluoride. If they're in an excited state, they can be bound together, but if they radially decay to the lower state, they push each other apart. Now, in the case of laser physics, that's really good because you don't want to have any lower laser state, otherwise you don't have a laser. If you have more lower laser state than upper laser state, you don't have gain. This is the same kind of situation that if you consider the molecular hydrogen or deuterium to be the lower laser state, then if you've made it, it pushes off from the surface. And that's going to be true for almost any metal hydride when the desorption is exothermic. The molecular species can't exist on the surface as a molecular species. It exists inside as an atomic species. Consequently, this gives you the mechanism, basic mechanism to have a phonon gain, phonon laser, exothermal desorption. Now, what's really interesting in the palladium hydride or palladium deuteride system is that at low loadings, hydrogen or deuterium wants to go into the palladium. Since it wants to go in, that means it doesn't want to come out. And that means when it doesn't want to come out, you've not got a possibility of making a phonon laser because the energy levels are reversed one relative to the other. That which should be your upper states, now your lower laser state here, so you have no gain. You can never have any gain in this region here. In this region here, it works very much like the graph that I just showed that was true for copper. At high loading, it works this way for palladium. And it turns out for high loading in nickel, it works the same way. It works, in the case of hydrogen palladium, you get the same kind of curve, but it's shifted over a few ticks. In the case of nickel hydride, you get the same kind of curve, but the crossing is closer to, I think, 0.5 or 0.6. Some metals never cross this line. For example, tungsten and molybdenum live up here, and so they exothermically desorb at all loadings. Some materials live down here more. Lithium hydride is down here. Titanium hydride spends most of its time down here, but titanium hydride at loadings somewhere near or above 2 goes into an exothermic desorption region. These curves are temperature dependent as well. At higher temperature, this whole curve moves up a little bit. At lower temperature, the whole curve moves down a little bit. And though the general effect's well known, having detailed data that's accurate for it, that's not so easy to come by. Now, one reason that that's so interesting is that if you look at some of the excess heat data from SRI, SRI's done this careful calorimetric work in the heavy water system trying to replicate the Pons-Fleischmann experiment. There's 2 or 3 nice features of their experiments. One, they have funding, so they can transfer large amounts of energy and all that. The second thing is given some funding that they had some time to develop some rather elaborate calorimeters. So they had closed cell calorimeters that were accurate or are accurate to better than 0.5%. And they're seeing effects that are at 10s to 50s of percent. So they have pretty good signal to noise ratio. Additionally, they measure their loading during their experiment such that they can plot their excess heat data on an axis that actually has a loading that corresponds to it. And what they see, I didn't plot it here, but at loading down here they see 0. The heat only occurs when they get high loading, and from my point of view, though this is an argument that proves you have a phonon laser, the conditions under which the SRI group sees excess power are the same conditions under which you would see phonon lasing. I talked to the SRI guys about this, and I mean, they've been following my theory work and been trying to either help or give me counterexamples, whichever way Mother Nature decides to go. And the theory also says that if you're in the exothermic regime and you desorb, namely you outgas rapidly, that gives you more gain, and that should make it work better. And I guess recently Mike called me up and he said, well, Peter, I've got some news for you. I say, what, you've shot down another one of my theories? He goes, no, we've got an example where we held everything fixed, the power was fixed, the current was fixed, and we got a spontaneous increase in the operating excess power. And they managed to correlate that with increase in desorption. They got two examples of that, and the correlation's very nice. So that was sort of a, almost a first in terms of getting a picture to look proper. It's, of course, probably worthwhile noting that back in 1989, a lot of groups tried to replicate the Pons-Fleischmann experiment. Pons and Fleischmann, of course, never plotted their data as a function of loading, and this wasn't known back in those days. But you can go back and you can look at the papers from many of the groups that tried to replicate it and had a little bit of trouble. And what you find out, for example, is that between the Caltech group and the Harwell group and the IBM group and the various groups that worked, that the loading, the peak loading that they got were in this region here, where the expected result, at least from these theoretical considerations, would be no phonon laser, no energy transfer, no gain, and so forth.